reminder, Jim. Okay, back in business now. So let's go back to my plant experience. So here it is. That vacuum system sat in the corner and you never had any problem with it, and so I never really understood how it worked. Well, I want y'all to go back today and know how a vacuum system is supposed to work and what it does. And this one's easy. If I probably had to pick the number one thing of making a good brick, having good vacuum is at the top of the list. Good vacuum is incredibly important. So let me think of it. I think what we figured out is maybe if I get either, well, you might, oh, here we go. All right, so how about a few rules for vacuum? So with few exceptions, and I need to change that, better vacuum results in better quality, period. Good vacuum is imperative to making a good brick in our world. All right, now then, this is simple. The goal of a vacuum system is to maintain a clean, cool service fluid supply for the vacuum pump. All this stuff we're going to talk about and the piping and everything else, that's all we're trying to do. We want a clean, cool service fluid. Okay, so think about that, and we'll talk about that in more detail. And vacuum leaks rob valuable capacity from your vacuum pump. You really need to search for these aggressively and eliminate them. And vacuum leaks are one of those little things that kind of creep up on you, that suddenly it gets a little worse and a little worse, and then suddenly it's creating a problem and making a brick, and you can't really find them. So the good guys really chase those down and really make and try and run with as much vacuum as they possibly can. All right. All right, vacuum. So here's another one. So there are two different ways to read vacuum. Okay. All right, and they are both related to each other, but I want to explain to you how it is. I still think most plants use a simple vacuum gauge, and so a simple vacuum gauge, when exposed to atmospheric pressure, should read 0. Okay, so we're just at, it is atmospheric pressure. That's where we are, and then as you start to draw vacuum, the numbers are going to increase. So the higher the number on a vacuum gauge, the better. And so somebody tell me what's typical vacuum in your plant. 28? 27 and a half. Okay, those are vacuum gauge numbers that I'm hearing. Okay, all right. Okay, and and you know what? And I know of one customer we've got who says that if it's less than 28, they will not set a brick on the car because they're going to have trouble having the green strength they need, but different material. But it's interesting to hear you say that. But okay, we're in a range. We're in a range there, though. So you're not going to set it unless it's 25 or better. But y'all run 27 and a half, and you run 28.
Well, it said if it's 25 or it hits 25 or looks like it's dropping, it's not good. But we have an average like say 27, 28.
Okay.
In that range, then we're good to go.
All right, and I will ask a question, and I'm going to get to a point. Is 25 in his plant the same as 25 in your plant? Or your? Yes. Oh man, you guys are on it. That's right. It depends on altitude, and that's one of the little problems with using vacuum. The atmospheric pressure impacts that. So altitude could vary, and so if those plants are at different elevations, you can't expect those the same thing to read the same. So that's why we're going to talk a little bit about an absolute vacuum gauge. And an absolute vacuum gauge works on the other end of the spectrum to where it should read 0 if you ever achieve perfect vacuum. All right? And I would tell you an absolute gauge is a more consistent and accurate way to measure vacuum. All right? And so let's talk about the way it works. Atmospheric pressure, and so all that air up above us, it's hard for us to think about, but it's creating pressure on it. We're not conscious of it because we're just used to it every day. But atmospheric pressure at sea level is 29.92 inches of mercury. Okay? And so what you're doing when you're using a vacuum gauge and you're getting 28 and you're getting 27 and a half and you're getting 25 or better is you're drawing all the way down to where you're that close to 29.92. So Now then, in an absolute gauge, we're going the other way. And so it's really 28 is essentially would read 2 on an absolute gauge. Okay, so you've got that one as well. And I think I just want you to know you can do both, and an absolute gauge is good. We found one finally, and how about this? This has come a long way. At one time you had these mercury U-tube manometers, and you had to add up what was on this side of the column and this one, and then it had mercury on it, and we weren't supposed to ship anything with mercury. So what we've got to is this one. See if that's in the next slide there, George. There you go. So these are nice little vacuum gauges. They're dependable, they work well, but they read vacuum directly. You don't have to calibrate them, and it doesn't matter whether it's at sea level. Y'all can all compare how you're doing regardless of what the elevation of the plant is. And yet again, even a vacuum gauge, depending even on atmospheric pressure, if there's a storm today and it's sunny tomorrow, the pressure in the plant's a little different. It doesn't affect these. And so I would encourage you, this is a good way to read vacuum and a little bit more accurate way in the long term. But I would also say this, you guys are 2 steps ahead of a lot of folks. At least you're reading vacuum and you know what it is and you've got a level that you're shooting for, okay? But we'll talk about 2 ways, vacuum gauge pressure and then absolute.
I guess that explains the difference between the readings, because we have a regular one that you're talking about, but it's always either higher or lower than
Well,
the reverse one.
And I'll see some of those vacuum gauges, and you'll see 3 in a line on a vacuum system, and one's out of whack with the other 2. They just don't always seem to be consistent to me, and it's like, but I'm just you really ought to have something dependable to be able to read vacuum, and how about this? I think about as good as I've ever seen is maybe 28 and a quarter, maybe. I don't know if I've ever seen anybody running with 28 and a half. 28 is really good. Can you do it? 28 and a half? Okay. I'll certainly say I don't know of anybody that's ever done better than that. Go ahead.
29. We run a consistent 29 over 30.
Oh, come on. All right. I might want to see that. Okay. Well, one of the things that I like having this conversation, you get some perspective of what's good vacuum, okay? And I am going to tell you, good vacuum is probably as important to making a good brick these days as anything. All right, let's go to the next slide, George. All right, we sell a double tank vacuum system, and I think just about everybody would have a double tank vacuum system. So double tank, one here and one here. All right, so there's some rationale for the way those things are made. That the purpose of the double tank, remember, a clean, cool service fluid. Well, we want to give that vacuum pump a service fluid to be able to operate. All right, first of all, let's talk about what do we use in the vacuum system. What's typical to use as a service fluid? Anybody know?
Transformer oil.
Transformer oil, that's right. And why do we like transformer oil? We like transformer oil because of the same reason they put it in transformers. It's got good heat transfer characteristics. We want to dissipate the heat out of that system. And so again, the cooler we can keep that vacuum system, the better our vacuum's going to be. And you got to keep it clean as well. All right, so now then, the overflow of this tank is really, the tank level here should be set with the center line of the vacuum pump. All right, oil comes back in from the cooler and it overflows back into this lower tank, and this is just really excess capacity or storage, but we pump out of the bottom of this tank and we circulate it through our cooler, and we're going to talk about that in a minute. Now then, what happens over the course of a day or the course of operation? What happens in this lower tank?
Water.
That's right, moisture and water. All right, and I think we were talking about this a little bit. Yeah, George and I were talking about this a little bit yesterday. So when you start drawing vacuum on something that's got water in it, we can boil water at room temperature when you draw vacuum on it. Well, what happens eventually is that water accumulates in this lower tank, and what you want to do as an operator is let's give that time. That water will separate from the oil, all right, and so the water's going to be on the bottom, You can open this petcock and drain the water off of it, and most people do it at the beginning of the shift. Okay, after it's had a little time to separate.
I do mine every morning.
Every morning. Okay, well that's the way to do it. That's the way to do it, because that water kind of gets entrained in that oil, and if you give it a little time, it'll separate out. We do sell something. We sell a dye, and somebody told me, I think what it was. You know, they dye diesel fuel, off-road diesel fuel, and I think it's the same dye that they put in that. But we sell a dye that'll go into the oil, but not the water. If you have a hard time telling the transition between oil and water, we sell a dye that you can use for that. But we do want to drain the water off, because water vapor is an enemy and really takes up the capacity of that vacuum pump. Okay, now then, I've got here's another one of those little things. Okay, so let's just say we've been running and the brick machine, well, let's say we get to the end of the day. Let's just say that we get to the end of the day. What we really want to do is, most people are going to let the vacuum off, and so that's what that vent valve is for. So we let the vacuum off of the vacuum chamber. We open the lid, and you're probably going to push down the sides and scrape the material off the sides of the vacuum chamber. All right, and then we'll cut the vacuum pump off. Does anybody ever have a wet filter? You ever get a wet filter? I'm going to tell you why. I'm going to tell you why that's happening. You've got two problems. There's two things that are happening. One is we've got a little check valve. We've got a little check valve in here, and a lot of times you can hear that thing clicking. All right. Well, that check valve, what that check valve is intended to do is, if you cut the vacuum system before you let the vacuum off here, your pressure is going to be lower here. So what it's going to do is want to suck the oil out of the vacuum system up and through your pipes. All right, but the check valve is designed to stop that oil from coming up the pipeline. But if the check valve's bad, and you've cut the vacuum system off before you've let the vacuum off the vacuum chamber, it's going to pull oil all the way up into that filter. So you actually got two problems. Check valve's bad, and for whatever reason, you're cutting this off before you're letting vacuum off the brick machine. So that's kind of the way that should work, but it'll tell you you've got a little bit of a problem. Let me point out another thing that's good on this diagram. And by the way, this is another free print. I think it's called VACSYS 001, but it talks about piping specifications and how we would want to see a vacuum system put in. If you'll look, you see we've got crosses in these lines. They're not sweeps and elbows. I spent some time in Australia, and I saw some nice stainless steel vacuum lines, and they had these nice long sweeps in it. We don't like sweeps or elbows. We like these crosses, because we'd like to be able, you're going to suck some trash in them. Well, let's make them so we can take the caps off the end, we can look down through them, we can take a rod and clean them out real good. I had a customer in the UK, they had a problem, they couldn't get vacuum. Problem. Well, what they figured out, they actually probably had an undersized vacuum system, but we talked about this. They couldn't clean their lines out, and when they went to disassemble everything and replace it, they realized that what was a line that was supposed to be that big wasn't big enough to slide a nut through it. It had just material built up on the sides. So that's the reason we want to make sure we can keep everything clean, because you just have things happen.
What would be a good way to clean those lines like that without jeopardizing?
Well, just they ought to be durable enough. I mean, and you see them made out of a lot of different things, but they ought to be durable enough. You ought to be able to take a rod or a steel rod or something and slide through them with something on the end of it and brush them and clean them out. They shouldn't, if it's done right, they really shouldn't be too fragile to where you shouldn't have to worry about breaking anything. But I would. That's it. Go back and take a look at what you got. You want to be able to look through them, and you want to be able to clean them out. Okay. Let's go to the next slide. I think that's all we've got right there. Let's see what else we've got. Okay. This one's easy enough. So I told you we're going to know how we're going to operate, or how these things work in the end. Before I get started, there's a way I do this, but let's talk right here. If you see there's a little gauge right here, that any vacuum system we built in the last 15 years, we put a compound pressure gauge that goes between the vacuum pump and this upper tank. And we really want that to read 0. All we're trying to do is give that vacuum pump the service fluid that it wants. We're not trying to force it in there. We're not trying to starve it. We're just trying to kind of let that pump pull service fluid as it needs it. And so that's a compound pressure gauge. Compound pressure gauge, typically you'd want to see it reading somewhere pretty close to 0. All right, now then, let's see. So here's the way I talk about the way these things work. You've got 3 motors on a vacuum system, and let's talk about what they do. That's the easiest way to do it. Well, your first one's going to be running your vacuum pump, and your vacuum pump's probably going to be 20, 30, or 40 horsepower vacuum pump, okay? So big motor's going to be running the vacuum pump, all right? Then the second one, you've got a motor down here that's driving an oil circulating pump, all right? And so remember, we talked about keeping a clean, cool service fluid, and so we're pulling oil out of this lower tank. This is pumping this up. We're going to go through a filter assembly, all right? And I think we've got a picture of this. I've got a picture of this later. But we go through that oil filter assembly, and so what we want to do is that if there's any dirt or trash in there, we want to pick it up here, because next we go up to an oil cooler, which is where our 4th motor, small little motor that drives a fan. It's just a radiator. That's all this is, where we're blowing air across fins and we're circulating the oil through that cooler. We're blowing clean, cool air across that, and then it comes back into the vacuum, into that top tank. So that's all it is. The vacuum pump's pulling de-airing the material in the vacuum chamber. All right, so we're pulling air out of the vacuum chamber. The pump's using a service fluid here, and then we're just circulating that service fluid and trying to get the heat out of it. At one time, I think this came about and was developed because folks were using water to run vacuum pumps. You can run a vacuum pump on water. The same rules apply. The water's got to be clean and it's got to be cool. Well, if you probably went back 50 years ago, and I'll still see it in certain places in the world now, that you'll see them running water to run a vacuum system, but they're running it out the back door or into the drainage ditch. Well, now environmental regulations and all don't want you to be running water out the back door and something that's been used for industrial purposes. So this is a closed loop system. But that's all it is. So a clean, cool service fluid is the way you work. So motor on the vacuum pump, motor running the oil circulating pump, and then you've got a motor on that oil cooler. All right, so let me ask you about the oil cooler. Where would be a good place to put that oil cooler? Right next to the wall? Okay. Next to the okay. Which is okay. I am going to tell you, let's talk about where not to put it. Don't put it on the floor, and don't put it next to sometimes I'll see them put on the floor, and I'll see them put next to a brick machine. Well, we want to have them put, you don't want it to be too far away from the brick machine because we don't want to have a real long way to go. But the coolers, we want to get it clean, cool air. So if you get it up off the ground, up above head height, there's somewhere to where it's not in the dust when the sweeper's running through it and blowing, it's sucking dust right in on those fins and all. We want to have it somewhere where you can get clean, cool air to that cooler. That's what we want to be blowing across the oil in the cooler. All right, let's see what else we've got, George. Okay, so we talked about the oil recirculating pump. And so here's the motor, here's the pump. We've got a dual filter assembly. I'll tell you what I like. I like going into a brick plant, and I like seeing dates written on those filters so you know when they change. The maintenance guys, I love seeing that because you know when it was done. But the other one that I'll tell you is that filter assembly will automatically bypass when there's a pressure differential of 15 psi. So if these filters get clogged up, it's just going to bypass them and it's going to go on up, so we don't starve oil going up to that cooler. But you're kind of messing yourself up because that dirt could be collecting inside that radiator up there where we're cooling that oil. So you got to keep a look on those filters. But this works pretty good. I think we've got a slide in here of that oil cooler.
Robert, one thing that Jeff told me, and I kind of do too, is like if your gauge isn't working and you go and touch that filter and it's cold, you probably don't have warm oil running through that thing. So, I mean, you know, you've gone into a plant and your gauges aren't working, that's something quick you can do, just to kind of do a quick check.
And then fix the gauges.
And change the filters if they're cold.
But good. Well, I've got a line on here. This is more efficient than the older MODINE coolers, and you'll see the older MODINE coolers kind of had rounded edges to them. They look like they're out of the 50s or something. But the reason these are more efficient is kind of the tubes that go through them are smaller. And so that is right. They're more efficient than MODINE coolers, but because you've got thinner diameter tubing that runs through them that lets them be more efficient, we've got to make sure that those lines don't clog up, and that's the reason we've got the filter assembly on there, and that's the reason you want to make sure you keep them clean so it can work the way it's supposed to. All right, let's see what else we've got. That's the sight glass on an upper tank. So at rest, you ought to see oil at the center line of that sight glass on the upper tank. Once you start running the system, there's so much oil coming in, there's so much turbulence, you won't be able to tell anything when it's running. But at rest, you ought to see oil in the center line of that sight glass. Again, there's the, we still sell today 15, 20, 30, and 40 horsepower vacuum systems. Probably for a 75 machine, we pretty much would quote a 30 horsepower system, and for a 90, a 40 horsepower system. We've got some diameters in here, which is always important if you happen to upgrade a vacuum system. We actually specify what should be the minimum pipe diameters running to it. And like I said, there's a print, and so if it's engineering or maintenance or anybody doing a project, call George or call us, and we can get you a print that specifies how that thing ought to be put in line, and it'll save you some heartache somewhere down the line, because like I said, we've learned from mistakes and people having problems in the past. Okay. Now then, we're going to talk. We're all the way up to the extruder, so we're working through here. Now then, let's talk about safety first. And I'm gonna. So this is good. We ought to talk about safety anytime we talk about doing anything. But I would like to scare you before you leave here, and I've got a couple video clips. I want to share. Let's go through. So we'll talk about safety, material level in the extruder, and an extruder speed. All right. So steam and pressure. So here are just a few points. So extruder amps. What we're typically using to run a brick machine is we're looking at the amps on the extruder, and you're looking at dial pressure, right? Those are kind of their two surrogate measures in a way to tell us what we're doing in that brick machine. But they do provide a measure of process control. All right. Now then, but what I want you to know is, and some folks have learned the hard way, soft material will not push hard material out of a die. All right. When you get hard material packed in a die, and a lot of times, let's say you got a problem, or you know you're getting ready to have a problem, and you hit the water hose. I'm going to try and save it and bring it back from the edge.
You're going to blow it open.
Yeah, and that's what we want to talk about. So augers turning in that brick machine without a column coming out of the front of it is a bad thing. We do not want that to happen. And I'm also going to tell you, one of the reasons I really want to talk about this today is we can't really put a safeguard on that machine to make everything stop. But if you've got augers turning in that machine and there's not a column coming out of the front that with material in there, that is a bad thing. All right. So what happens is friction. Yeah.
With that situation you just said, could there be like a pressure valve that would kick off and release the pressure on it until you could get things going right?
Well, what you're going to have to do is you're going to have to open that die, and you're going to have to dig that die out.
Dig it out.
It isn't so much. It is the pressure and what's going to happen to that pressure. But you talked about. I mean, you could open your vacuum valve and relieve the pressure that's created. But let's think about that. You remember out of science class, friction generates heat, and heat causes pressure to build because we've got a fixed volume. So as it gets hotter, PV equals nRT. when time, something's going to give. And let's go to the next one. Let's see if this thing will play, George. You may have to hit it twice. This is the one I want to make sure my links may not be right. And hit it one more time. See if you can hit it one more time. Okay, so let's go back. Jim, let me walk back to the back of the room. This is one where we may have to go out to that file folder and we'll just play them manually. All right, so let's go. All right, so clip at the very bottom. Let's click on that one. So this is from a customer in South America that was nice enough to share what they had happen. Watch this machine. So these guys, this is a little different operation. They run these machines remotely from a control room. It's a pelletizing application. I think this thing cycles through again. But that is what I just described to you. So they wound up, got hard material in the die, continued to turn it, and that thing went off like a bomb. And we have had, and how about this? My line, I don't know how many of you ride motorcycles, but my line is everybody that rides a motorcycle's got a story. They may not have had an accident, but they've got a story. I think just about what I'm learning is everybody that runs a brick machine has got a story when we start talking about this, you know, that hopefully you didn't get hurt. Jim, play that next one up above. I've got a second one, and we'll do that one as well. This one's got a shear bolt on it. This is a 75 machine, and these guys are loosening the shear bolt, and this slowed down, and this is in slow motion. But they're trying to break that shear bolt loose on a 75 machine. Okay. All right. So there we go. And Jim, if we can get back in the presentation now. I think I must have managed to break my links in there somewhere. But that's the two that we had embedded. And so let's go to the next. If we go to 40 here, click on that one, and we'll pick up from there. All right. So now then, what do I want you to take away from that? So a load control, a Model B load control, or, all right, so if the amps get high, you get an audible alarm, or it disengages the clutch. If you're running a 75 machine, you might have a shear pin. Those things protect the machine. They do not necessarily protect an operator, okay, from that situation that I just showed you. And so that's the reason we've got to talk about what is the right thing to do and what's the wrong thing to do. All right, so what I need you to know is do not continue to operate the machine without producing a column when you've got material in the vacuum chamber and you know there's material. And slide the die over or open the hinge door, clean out that hard, dry material, run some softer, wetter material inside the machine, close everything back up and start making brick again. Where people get in trouble, and I know it, I've seen it, hitting the clutch, right, and reset. Hitting the clutch, reset, bumping that thing. You know, that's where you get in trouble. And I'm going to tell you, we had some, not in Acme, but we had some folks a few years ago had one of these things happen, and somebody got hurt. Luckily, not fatally, but I think there was a broken arm by the time they were done. But I want to tell you there were a couple things, and I want you guys to all be better in this. By the time all was said and done, those guys that morning had been they had been on the floor for an hour and a half and they hadn't made a brick yet. Okay? So they're sitting there, that's what they got to, hour and a half, and they hadn't got a column out of the front of the machine yet. Second thing is I don't think they had a person on the floor that had more than 3 months of experience. And so there's no substitute for experience, but I just want to tell you, let's talk about the right thing to do. You can get yourself hurt, you can get somebody else hurt. If you wind up getting hard material in a die, take your time, slide it over, open it up, clean it out, and get going again. So there it is. There's the safety message with an extruder. We don't want to see anybody get hurt. All right? Now then, let's talk about augers and liners for just a little while. I just want to let you know what is available and some options. So we've got 2 basic sets, and we've got dozens of variations past this. But an HCV set, and CV stands for constant volume. And where we will typically see or think that a constant volume set works better, if you have a fairly plastic raw material that's got a high clay content to it, a lot of times we think a constant volume set works fine, and that's really the right match to a really plastic raw material. The other basic option that we have is a compression set of augers, and we call those HTR sets. So if you're ordering or want to know, you can look on your invoices and you can see they'll either be labeled in the description HTR or HCV. And an HTR is that as you go through rotations in the barrel, we're actually compressing that material. So, and where we, as a general rule of thumb, where we see those work better, or what they were designed around, is a shorter raw material or something that might have more of a shell, something to where you really need to put a little bit more pressure and compression on that to make it hold together. So a constant volume HCV or a compression set, which is an HTR set. Those are the 2 general rules. But I'll just say again, I use that phrase, it's a general rule, and it can, those rules don't always hold, and sometimes experimenting with both will tell you something. So, all right, so let's go to the next slide. We've changed the lip on them a few years ago to where we now virtually, I think everybody that's running a 90 brick machine is running what we call an EW or extended wear auger. And we changed a couple things about the way we slick augers, but also by changing that lip. In general, the general feedback was the life of these was 20% better than what it was with the older ones, and we've had really pretty good success. So there's just a change that we made with that a few years ago. Let's go to the next one, George. Liners. Okay. So the augers are chrome, and then the liners in the barrel are made out of chrome as well and are made to be replaced. All right, I want you to know that there's 3 different really versions of those. Is a spiral, and a spiral looks like a rifle barrel, and that material will kind of slide inside that rifle barrel as it goes through. And those liners provide the least resistance to clay sliding through that barrel. The next is wedge. I would imagine we may have as many more customers running wedge liners as anything. But a wedge is kind of the middle ground of resistance, and it's going to kind of, again, check that material with rotating in the barrel. And then the most resistance would be waffle liners, and it's unusual to find anybody running a waffle liner. I didn't list them up here. We've also got some smooth liners. We've had a few plants ask questions. Jonesboro at one time had, I think they had problems with hard caking up there. Yep. And I think, I don't know, do y'all run a mix of liners up there? I'm not so sure if you still do or not, but that problem has kind of gone away now, hasn't it?
Yes, it has.
Okay. Now, we may talk a little bit later, but there are different liner choices in addition to different auger choices. All right. We talked about at one time that L1 liner, which is a liner that goes in the very back of the barrel. For a long time, we only made that in ductile iron, and we were really worried about, I guess, chrome breaking. We've done some experimenting and now offer a chrome L1 liner. And as we talked about earlier, chrome's got much better wear characteristics than ductile iron does. And we talked about sealant augers backfeeding. Well, you really don't want to see an extruder doing the same thing. And as augers and liners start to wear, you'll start to see that material rolling back in the vacuum chamber. And we really don't want to see that either. But this is better. This is an improvement we've made in the wear life on our liners. Okay. Feed roll shaft, and this is just a reminder, where so this is your feed roll shaft that runs parallel to your augers. Some people call this a packer shaft. Which are the swipes that are going to wear the most? Probably up here at the front a lot of times, the ones that are hard to see, and you've got to take a cover off to really, and stick your head in there to really see what they look like. But I've mentioned this and just have it in here, out of sight, out of mind. And I know that in the way this is made is if you happen to bind something up, this is actually made with shear pins in these couplings to where you'll shear a pin in there. So rather than tearing up something in the gearbox, we'd rather shear a pin out here. That's something we can work with and easier to repair than getting back into the gearbox. We've had customers that have sheared pins and didn't even know the feed roll shaft wasn't turning. They couldn't tell a difference. Other folks just right off the bat talk about it making a difference of 2 cuts a minute or better if that feed roll shaft is not working. So I would just remind you, and George will talk about this a little bit later, we've got some grease points on here, but I just would encourage you. This has got feed roll. This has got tips on it. Keeping all this in good shape is generally a good rule of thumb, and for most folks is important to be able to keep the material rolling through that brick machine. Okay. We do have an auger puller. The augers are made to where you've got an indention in them, that you can hook them and slide them out the front. So that does. We can talk about that. Just good to know that we do have it available. That makes it a little easier changing augers. And that's really what it looks like assembled, to where you can kind of jack them or pull them off the shaft. Some folks, can you run them out of your machine? Can you extrude them out the front of the machine, or how do y'all change them?
Pull them out.
You pull them out? Okay. Do you use this or something else? Brute force. Okay. All right. Very good. All right. You remember we had that image of what a pug tub level should look like? Well, I'm going to do the same thing with the extruder. The image on the left is what we would consider the extruder to be starved. When I look down in that vacuum chamber, I really don't want to see a whole lot of the augers back there I don't want to see a whole lot of the augers in the vacuum chamber. We'd really like to see those covered. All right, now then, I'll tell you what the reality is though. All right, so an operator really doesn't want to back up that vacuum chamber and have to get in trouble and have to dig it out. So I remember James always liked to always see the little glint of that auger wing every couple rotations, being able to see that as it came around. And I know that's where most operators probably like to be. You don't really want to see a brick machine like this. And this may be a little bit exaggerated, but it really would be a better way to do it. We really want to see a brick machine. You're going to get the best performance if a brick machine is run full or with full augers. So this is much closer to what we would be, what we really want to see a brick machine done. Operated is not starved, but really having those augers full. And we're going to talk about why that's the case here in just a little bit. All right. And so here's kind of the line that I want you to take away. So there is a correct auger speed for a given product and desired production rate. So there is a certain speed that machine should be running, and to give us that condition, really what we saw over on the right-hand side of that slide. All right? Now then, we're going to talk a little bit about extrusion efficiency, and I don't want you to remember a bit of this. I'm going to walk through an exercise. It's good to talk about. You don't have to do this. You're not going to be doing it tomorrow. Don't worry about it. Just listen to me for a little bit. So extrusion efficiency. Let's talk about that, what that is, and how we calculate it and how we can use it. All right? So extrusion efficiency is actual volumetric displacement per revolution divided by the theoretical volumetric displacement. So the number there on the bottom is easy. So I've got a chart and I can tell you for a given auger set what that theoretical displacement is. The number on the top, the actual volumetric displacement we can calculate that, and I want to tell you how we can do that. So we can calculate that by if we have a tachometer and we measure the column speed. That's easy enough. We can check that, or we can count cuts per minute and know how long the slugs are too. We can do it that way. And then we measure the cross section of the cap and we correct for the void. And then we can count the coupling, how many times the coupling's turning in 30 seconds and multiply by 2, or count it for a minute and see how fast the auger's turning. All of that, we can calculate the actual volumetric displacement. So if we've got those two numbers, we can calculate an efficiency. Well, we're going to do an example here. And this gets back to my point is we'd like to see a machine operated with full augers. So let's go. This is what George does and will do. So I mentioned that we've got a chart, and so here it is. So if I know what augers you've got in the machine, I can tell you what the theoretical displacement of those augers are. So there's the chart. Easy enough. So there's one number we've got. So we go into the plant and we've got a tachometer and we figure out, well, we're running at 115 feet a minute, and the auger shaft is running at 38 revolutions per minute. Column size is 3 inches by 10 1/4, 25% void. Slug length 32 brick. Got a little waste correction there, or we've got a waste piece, this waste slug there. We're cutting 14 slugs a minute and we're running CV augers. Well, this is all the information we really need. This is everything we need to be able to calculate extrusion efficiency. Okay, so let's go to the next slide. And as they used to say in math class, it's just plug and chug now. So we can take those numbers and we'll plug them in. 115 feet a minute. We're going to correct back to inches again. 3 inches by 10 1/4. That was our cap dimensions. All right, 75%. So that's 1 minus 25% void area. And we divide that by 38 revolutions per minute. All right, so 837.5 cubic inches per revolution that auger's turning. All right, 837.5 divided by 2050 cubic inches per revolution is the theoretical number. We get 41%. 41% good or bad? I don't know. Doesn't sound too good, does it? But really, it's all relative to a particular product and a particular machine, a particular material. I will say, I know from experience, because we've done this enough, that number is low. That number is low. But how do we answer that? Are we really running this brick machine the way we should? Well, there's a way we can find out. All right. So what if we run some material into the vacuum chamber to where we know those augers are full? All right. So we're going to run the pug without running the extruder, and we're going to run material about halfway up into that vacuum chamber. And then we're going to start both machines, and we're going to put that tachometer back onto the column again, and we're going to see how fast it's going. All right. If the column moves a whole lot faster than it did before, what does that tell us? Tell us we were starving that brick machine. That what's holding back that brick machine is how fast material's coming into it, not what the machine's actually capable of pushing out. So let's go to the next slide. I might have gotten ahead of ourselves. So there it is. Question: can we slow down the extruder and still meet our production requirements? If we need 14 cuts a minute at the setting machine, we don't want to mess with that, right? That's what the setting machine needs, and that's what we want to do. Our question is, are we running the brick machine at the right speed to really do that the best way we can? So here it is. Under the existing conditions, we're getting 14 cuts a minute, 98.5 inches per cut, or 115 feet a minute. Well, when we fill the vacuum chamber and we started everything else up, column speed jumped up to 145 feet a minute. So what that indicates, we are really starving that brick machine. You remember that image over on the left-hand side of that slide? That's what we're doing. And what we really want to do is get it to where we're running the way it looks more on the right-hand side. So George, let's go to the next slide. So what is the right speed? How can we use that information? And by the way, if you ever wanted to do this, that's what George is here to help everybody do. So we know we can push out 145 feet a minute if we're running at 38 revolutions per minute. And so by simple math, we can push out almost 4 feet of column per revolution of the auger shaft. We only need 115 feet a minute. That's the right speed for the setting machine. We don't want to mess with that. But what we're going to do is we're going to use this and figure out if we just need 115 feet a minute and we can push out 3.82 feet per revolution, we should be able to get the exact same thing running that machine at 30 RPMs. So we can slow that machine down, and it hadn't impacted what's coming out of that machine at all. What I want to just tell you, that machine is over-speeded for what really we need to be able to do, and you get a better result. And I always look at it like this. If a brick machine's not running fast enough, somebody's going to yell and scream and stomp their feet because they want to make brick faster. That always gets fixed. What a lot of people don't realize, you can run one faster than you need to, and a lot of times people don't realize that's not really right either. There's a happy spot to where you want to run a brick machine. Now then, let's stop. If we've got a VFD on the machine, this is easy, right? All we got to do is just take that VFD and slow that extruder motor down, and that's simple. If we don't have a VFD, then it may be making a shiv change or doing something else to be able to make that change. So let's go to the next slide. Why is this important? And what do you get out of doing it? Well, so one, really you've got less auger wear for the same production. And here's the way I look at it, is when you're starving a brick machine, a lot of that material is getting in contact with an auger more than once. And so you do really wear out augers, to me, prematurely. The other thing they'll do, a lot of times if you're starving a brick machine, you'll build up unnecessarily heat in your column. And we're going to talk about that a little bit later. So you can lower the column temperature, you get a more uniform column density, and a more consistent column speed. A lot of times you can tell if you've ever got a tachometer or you even sit and watch a column, sometimes if you see a column surge, to me that's an indication you're starving a brick machine. So a more consistent column speed and a longer bearing and gear life. So simply you're turning less revolutions for the same production. And the only thing that I would caution you about is higher available torque could exceed a machine design safety factor. So what does that mean? If I had 500 horsepower on the machine and I was turning it at 38 RPMs, and I slow it down to 30 RPMs and I've still got 500 horsepower, I've got a whole lot more torque on that machine than I did at 38. So if you really wind up slowing one way down, you kind of got to see what the applied horsepower is on it, because you could wind up with a whole lot more torque and have gearbox failures and stuff like that. But I want you to just take away, if nothing else, we talked about what the material level ought to look like in a pug. We've kind of talked about what you'd like to see in an extruder, and it's something kind of in your day-to-day operation you'd like to see if you could achieve. Okay? All right, we're going to jump right in. Let's talk about die design for a little bit. And this is good. I think our friends this afternoon, I'm sure, are going to talk about this as well. I just want to talk about die principles. And I think a lot of people probably don't understand what we're trying to do at the die. And that's what I would like you to be able to leave here today, is understanding a few things that just the principles and what are we trying to accomplish at the die. It's like everything else. Once you kind of break it down, it's not that complicated. But I kind of want to give you some frameworks to think about what we're trying to do. Let's see. Controlled compression and flow while minimizing internal stresses. And we're going to talk about minimizing internal stresses here is what we're really going to talk about. So let's go to the next one, George. All right. And really what we're going to talk about, and what I'm going to spend the majority of this piece talking about, is die balance. All right? And poor die balance results in internal stresses. Internal stresses results in crack and final product imperfections. And does everybody know what I'm talking about when I use the phrase die balance? Okay. Well, we're going to talk about that, and that is okay. I want to get everybody on the same page. Let's go to the next slide. That may be the best one to be able to indicate that. Die balance, really what we're referring to, what we want to see is we would like, if you put a splitter frame, on the front of a machine, what you'd really like to see is all those little segments of that column coming out even. That's exactly right. That's what we want to achieve. That we'd like to see them all moving out at a constant velocity. We don't want to see the center moving faster than the edges. We don't want to see the edges moving faster than the center of the column. We don't want to see that column taking a right turn into the floor or a left turn into the floor heading up towards the ceiling. We want a column moving straight at the same velocity. That's the goal that we're trying to achieve. And what we're going to spend the next 10 or 15 minutes talking about are what are the things that can impact die balance. But mentally, what I want you to think about is this is really what we're talking about in regard to die balance. Take a look at that middle picture, and what do you see there? Yeah, the center is faster than the headers on that. Okay, that's right, and we want to correct that. And I think I do have it on here that I said, the general rule of thumb is no more than 2 inches and 4 feet. And I'm also going to tell you there's 2 ways to do this. At one time, how many times do you come up with a simpler procedure? At one time, it was always, okay, well, you run it out 4 feet and you take the tape measure and everything. Honestly, we got into believing now you don't really have to put a splitter frame on the front. You can literally engage the clutch and bump that column out and a short distance, and you can look and see what's happening and usually tell whether or not you need to make adjustments. So think about that. This is what we're trying to do. Everything that I'm getting ready to tell you from this point forward are things that affect that die balance and may affect how clay flows out of the front of that machine. But this is the answer. You really want everything moving perfectly even. And it's just really interesting. You get into different products and different materials, the answer is different depending on where you go. But this is it. This is the essence of what we want to accomplish at a die. But bumping that die out and seeing what's happening with those speeds is really the answer. Let's move to the next slide, George. Okay, quick summary. Die holder length, the total length of the die base, the rear opening of the die base, lubrication, internal geometry, and bridge design. And let's start ticking through here. I think Steve added some in. So here's a little one. One of the things, you've got a telescoping. All the machines have a telescoping die holder. So you can move the die away from the machine, or you potentially could move it closer to the machine. But moving the die closer to the point auger should speed up the center relative to the outside. Moving the die away from the point auger slows the center relative to the outside. So one of the tools that you've got available to you is changing the position with using that telescoping die holder and loosening those 4 nuts and letting that thing move out a little bit is one option that you've got available to you to impact what that column or that velocity looks like coming out of the front of the die. Okay. Okay. So a shorter die assembly, and these are 2 little sketches here. So a shorter die assembly can improve die balance for slow centers, and it can reduce extruder amperage. All right. Whereas a longer die can improve die balance if you've got a fast center. So you've got more friction around. A longer die kind of creates more surface friction around the outside. So it isn't something, but there are different options for die lengths, and so every now and then we'll have somebody that runs a 6 or an 8-inch cap as opposed to a traditional 4 1/4 inch cap. So those things can impact die balance. All right, so just to sketch a few of the options that we have and some varying lengths. Let's go to the next one. Just as a general rule, The die base rear opening should be 2 inches smaller than the auger outside diameter for effective lubrication. You need to get some compression at the rear of that die base, and so that's the way we look from looking from the bottom. So the rear openings are always a little bit smaller than what you've got at the coming off the point auger. Point auger in a 90 machine is going to be 18 inches in diameter, so the rear of the die base is going to be roughly 16 inches. Lubrication, and so this is a big one. All right, so one of the things we talked about, stiff extrusion, and that's what everybody's doing here. And so we lubricate the dies, and honestly, it's one of the measures that you're probably using is maybe your back pressure or your oil pressure on your die is one of the things that's telling you how stiff that column is. But what we're doing is we're just trying to create a thin film of oil that slides between that clay and the surface of the die base. That's all we're trying to accomplish. But depending on whether or not you're using oil or not, and it impacts that velocity profile coming out of the front. And I'll say this, lubricant should stay on the surface and should not penetrate the column. If you ever see oil running out of a core hole in a brick after it at the setting machine, you've got something wrong. That should not happen, because it's just on the surface. That's the only place we want the oil. If you're driving oil into the body, something's not right. I don't think this is as much of an issue here, but it is in certain parts of the world. We just do not believe in diesel fuel as a good lubricant. And this is something we always believe. If you're using something for a die oil or a die lubricant, slide it between your fingers. Is it slick? I mean, that's really what we want to accomplish. It ought to have a little slick to it. You know, and there are petroleum-based oils, and then it's interesting. A lot of people today are going to some kind of soaps and different things. And I would just be, how about this? I did environmental work when I first got out of school, and I'm certainly conscious of it, but I'm a little gun-shy on believing that some of the substitute lubricants really do as good of a job as oil does. I'll just say that and let everybody make decisions for themselves. But what we really want is a good slick surface just between the outside of the die base and the clay sliding through it. Yeah?
So how would, if it's not consistently lubricated on the die that's coming out, how is that going to affect the way that it strains the brick or whatever?
Well, and how about this? Let's. I'm gonna give you this one. What if we weren't lubricating on the left-hand side of the die, but we were on the right? Well, what I think it's going to do is the material's got less resistance on the right, so it's shooting out on that side, and it's necessarily going to move slower on the left. So I mean, I think you might have a column that's going to want to take a left turn into the floor.
So it has the potential to dramatically affect
Yeah.
the quality of the brick.
Yeah, that's right. And by the way, and the other thing from a philosophical standpoint, we really like getting lubricant on at the back of the die and letting that oil work its way out towards the front. If you're just putting oil on near the shaper cap, well, it looks good coming out the front, but I don't think it's really doing the work for you. You really want that oil on the column at the back of the die, bringing it forward. So there's another little point. Let's see what else we got in here, George.
What do people use for dye? What's everybody using? Vegetable oil. That's BC 110. We're using Elgin 10 weight, right?
Okay.
10 weight. Is anyone using anything else? All right, sure. Vegetable oil gets real sticky. I remember trying BC 110. That made the column get squirrely.
Well,
I remember that stuff, but it's different, you know, depends on.
This is
Soap.
so.
You used to use soap.
Well, it's just something you need, something you can depend on, and it's kind of. And I'll use this analogy. It's kind of like buying a really expensive a really expensive car and skimping on the oil that you run in it. You know, it's like, is that really worth it in the end? If you've got something that works and you can depend on it, does a good job, it's fine. But it was like, this is pretty important, having something that you can control. Yeah.
So it's better to have it come in at the front of the...
And think about this. Let's put it in at the rear. We want to put it in at the rear, and then if everything's working well, that oil's going to slide right along that column, and you're going to see the thinnest of films on the surface of that column when it comes out the front of the die. But and if we don't put oil on, or if we're oiling just at the front of the die, then really that oil's not helping you as that oil slide until you get up to that point. We really want to oil at the rear, or put most of the oil at the rear, and then just put a very small amount up at the front if we can. And we're going to talk about that a little bit too, kind of how that works. Now then, this is easy. Again, and none of this stuff is hard, right? Nothing hard about a vacuum system. None of this is too hard if you know what you're looking at. But look, let's think of it like this, and we're talking about oil. And remember what I said, we're going to put oil in the back, and we'd like that thin film of oil to flow out with that clay right out to where we can feel just a little bit of a film on that column coming out of the brick machine. And by the way, remember we talked about early column temperature? A high column temperature is another indication you got a problem somewhere. We really like to see a low column temperature, one that you can keep your hand on. A hot column is not a good thing, and to me, good lubrication should be able to help with that. All right, putting that oil on at the back, what we want to be able to do is we would like for that oil to be able to go all the way out. So when you've got a transition, and this is true regardless of whose die you're running, doesn't matter, but as you go from one section of the die to the next, you want this section, this opening, to be slightly larger than this opening. Okay, and the reason for that is let's go over and look at the diagram on this side. If this front section, the clay's moving this way, if you've got this situation right here, you've got oil and you got it, you did a good job, you got it on back here, and it hits this, and it's just like hitting a wall, and it just scrapes all that oil off, and suddenly you've got all this turbulence inside of your die and just chaos. But if you've done it like this, and this is exaggerated a little bit, but if that oil's in there and you open this section up a little bit, that oil just continues to flow all the way out the front. Now then, let's look at that picture in the middle. And actually, I think Jeff Koger said this was one of his plants. I think he said where he worked, and so he might have been the one responsible for this, which is kind of funny now that the picture's in here. But you've got a die base in the back, and what you're looking at here is this is a shaper cap. All right? And so the shaper cap, the die base is worn, and you've been running the die base for a while, and as it wears, that front opening of the die base continued to get bigger and bigger, but I was still ordering the same size rear opening shaper cap to mount on it. And this, what you've got here, is what we're showing here. That oil flows through here and boom, hits that wall, and you've just got chaos happening. So not only have you got problems with wear, but also trying to get that die balanced. I mean, this is where we create extrusion problems. And so this is what you always want to do. And what we encourage folks to do is if you're, let's just say you can run a die base and maybe you can run 6 shaper caps on it before you wear out a die base. What we really want to do is open up this rear opening so that we don't get a situation like this. We always want to have this type of transition. It's one of those just little things. But think about it. Don't want to scrape that oil off. We want it to ride all the way out the front of that shaper cap.
I know I was guilty of it. I would just call an order. I would say, give me what you got the last time on a shaper cap coming. And after a while, I didn't even realize it, but it was doing the same thing. And then I think it was somebody pointed that out to me, and after that I started measuring the opening and telling the person I was ordering this cap from what my opening was so that they knew to compensate for that.
Yeah, so the front opening doesn't change because that's the size we need the brick, right? So as long as the shrinkage is staying the same, front opening always stays the same. But you might have, if you're running multiple shaper caps with the same die base, you might need to open up that rear opening of those shaper caps. All right, so simple explanation. We'll talk a little bit. So we've sold a ton of these throughout the years, and they're very they really have worked well. But it's you've just got a single pump, and this is really good for oil control in the back of the die or the front. But the one thing to remember, especially today, is if you ever get away from a petroleum-based lubricant, you can't use this. The insides of this pump they'll rust up, and they just won't hold up if you're running a water-based lubricant. So it's the limitation. But a lot of plants have used these years and years and have used them very well. But we've come up that we do have another one, which is actually the V2 pump. And so let me tell you the advantages of this. So one, you've got one pump to where you can control the flow and the pressure at the rear of the die and at the front. So one pump, but you can control die oil pressure, different die oil pressures at the front and the rear. And the die oil pressures at the back, if you're putting oil at the back of a die and you're putting oil on, let's just say what we would call a mid base, the pressure at the mid base is typically not going to be as high as it is at the rear. And here's what you need to know about oil is it's always going to flow to the path of least resistance, right? And so it's better if you're actually lubricating in more than one place along the length of a die, it's better to have two separate pumps or two separate, the way to separate control over those two. Otherwise, your oil is always going to go to one place. But these work well, and the other advantage of these pumps is you can run a water-based lubricant or a petroleum-based lubricant either way, but they're good pumps.
On that V1 you had up there.
Yeah.
Is it best to have it low?
Great question. Great question. Let me give you the answer to this. All right, so on the pressure side, after it gets to the pump, I think these bypass at 1200 or 15 psi. They can really pump and get a lot of pressure behind them. But what they don't have is much on the suction side. So you ask a very good question. So you always want to have your oil supply on these above the pump itself. So you don't necessarily have to set the pump low, but you have to make sure that that your supply is above the pump itself. And that's a great question. I would have forgotten to add that. But yeah, it's a little thing. And George, that's actually even the V2s, I think. That's true with the V2s as well, isn't it?
Yeah, I think that's right.
Yeah, but good question. Good question. So you don't necessarily have to have the pump low, but you do have to have your oil supply above that so it can gravity feed down. You know, one of the things that we can use to influence clay flow through a die base is we can either cast in or create the geometry in with bulges. And sometimes you have a material that doesn't want to fill out the headers particularly well. And so what this does is kind of force material into the headers, but we can change the shape, the size, and the location. So that's one tool that we've got in development in influence and die flow with the internal geometry of a die. Yes.
Maybe I'm going back too far. I thought maybe you're going to come back around to, you mentioned the temperature of the die. What is a good range for that?
What would you say? Up to about 120 or so column temperature?
I've seen some 130. I've seen some that were spitting steam, and they almost looked like they were blistering when they were coming out. And I shot the temperature with the temperature gun, and they were up in the upper 170s. That kind of scared me a little bit. But I mean, if you can put your hand on it and it's not hurting your hand, usually if I put my hand on there, I will try to feel to see if there's oil, good lubrication around the whole column, and I can't keep my hand on there to do that. That's got me concerned. I mean, there's something going on.
So somewhere between 100 and 130 degrees if you were using a temp gun, and that's really what George's indication is. If you get up above that, it's going to be uncomfortable to keep your hand on it.
Yeah.
And what you get is, just think about that. That heat's got to get out of there somewhere. You're going to cause crazing in that crazing.
The exterior to dry too quick,
Yeah.
and the interior will keep some of this moisture, and so it'll
You got differential drying, and that's right. And and again, that's going to vary a little bit with material and everything, but it's one of those things, if we can avoid that and eliminate it, you're going to be better off. Yep. Okay. Let's see. Okay, so a ton of ways to you can influence die flow a lot with bridges, and we've got a couple different options. Not many folks run a rear mounted bridge. Most people run a throat mounted bridge, and here's the advantage of this. So if you think about it, and so friction, right? We've been managing friction. That's why we're lubricating the dies, to reduce friction. Well, if you've got these long pins, that clay's sliding across those pins for a lot longer period of time. And so if you can get away running a throat mounted bridge, that's probably going to be a better option. Plus, the other thing that you have, if you can run a throat mounted bridge, those pins are shorter, and so they aren't going to tend to flex as much. And so it's a little easier to keep those pin positions, keep those pins in the right position. And so anyway, throat mounted bridge is typically more popular and is better because they'll less amperage and more rigid pins. Okay. Little thing, but this is another one. If you didn't know this or don't think about it and can go home and remember it, you're going to be better at it today. Core tip position relative to the front of the cap. So they should either be flushed or recessed 1/16 of an inch. And we could spend a day and a few beers talking about why it happens. But if you ever have your core tips extending outside the front of the cap by that 1/16 of an inch or anything, it does funny, strange things to the clay flow. I mean, it is just like throwing a bomb inside of there. And I've seen, I don't know why, it's a small thing, but it makes a huge difference. Core tip should either be flush or recessed about 1/16 of an inch. When you put a bridge in, put a straight edge on it and make sure that it isn't sticking out outside of the cap. Have you ever experienced that before? You always do it right. Okay, that's good.
One person called me and they thought their cap, that they had gotten a cap that was the wrong size, but their cords were sticking out just a little bit and it was causing it to swell. And they were trimming off a whole lot more. So when we started looking deeper into it, they were sticking out about an eighth of an inch. Not much, but when you put straight edge on it, you can tell that. Somehow they put washers behind their core tips and brought them out, and they weren't sure why that happened or who did it, but they went back and fixed it and ran it, and they said that everything was much better, but they thought that something had changed in the size. It's a subtle little thing, but it's got big implications. So this is a good slide. The one thing that that we can do too. So if we were talking about having we can talk about having a fast center. Well, if you had a fast center, one of the things that we can do is you can put sleeves on your pins. And this one has actually got it, the way this is shown, you've got a little larger sleeve on that center pin. And the cores on that one are all the same, but you've got a little bit more resistance and it forces clay out to the outsides a little bit more. So those are one of those little tricks, you know, for altering die balances, is you can change those sleeves, diameter of the sleeves. I would just be conscious of the geometry of cores is another one of those things. The taper on the cores, the length of the cores, all can influence die balance as well. You know, I've got a slide in here on silicon carbide cores, and so these are compared to a ceramic core, the wear life is a whole lot higher. And actually, I think the price has come down to where these are very competitive now. So I would just encourage you, from managing costs, I think this might be. Let us price these if you're interested in trying some. But the silicon carbide cores are really a superior to the traditional ceramic cores. And
and I think I want to just tell you, I think I just want to tell you of the first fundamental when we're talking about dies. It all comes down to die balance. And if you can get that right, then you're going to eliminate a lot of problems, and you can let the kiln guy figure out what's wrong in his end of it. If you can do the things that we've talked about and eliminate those variables and have good die balance, and we would be glad to help if we could. But that's really what it comes down to at the die, is the things that we've talked about, and we've just talked about some options for controlling it. And this is going to be, I'm going to make this part really quick. Where are we with lunch? We're about at 12, and we're running a little longer than what I thought we would. But
11 o'clock.
Oh, 11. You know what? I've got I hadn't changed from Eastern time, so that's the reason okay, so we're doing better than I thought we were. Sorry, that's good. Let's. I'm gonna tick through. I'll tell you what we think is the best die we make today is our L die, and I'll keep this short, but because I really didn't come here to sell you anything, but I do want to let you know kind of how what we have and how it works. So one of the good things about this, you see these screws, you can adjust that bridge on the fly. If anybody is running an older K die, the K dies are inexpensive and very serviceable for a lot of folks. But the die, the bridge is pretty much where it is in a K die, and if it doesn't center up, then you kind of got to dig it all out and try and get it centered. Here you can adjust the position of those bridges on the fly with this one. The other one, and go to the next slide, George. I think so. There's the breakdown. The way this one also works is you've really got, actually go back one, and we'll come back to this one. You've actually got a die base, the red part is a mid base, and then you've got a shaper cap. And so it's really 3 sections. We're putting the outside of the die now is really the way we build these, is the outside is ductile. We were talking about material that is really strong, but doesn't have the best wear characteristics. So what we put on the inside is a liner that's made out of chrome. And these dies can be relined if you want to reline them.
That's from the K die.
On the L dies. The K dies are just a straight chrome die. So all of that's made out of chrome, and every now and then you get a column pretty hard, and every now and then you can pop a K die, you can break one of them. These are a lot harder to break because it's a chrome liner inside of a ductile shell. The other thing that's nice, and I'll show you in the next picture, the way the bridge sits in a pocket in the die base. And so if the way it's made is you can take the mid base and the shaper cap off, and that bridge is sitting right in there in that pocket. It is easy to change out. You don't have to dig it out from the back. So this is one of those nice things. Let's go to the next one, George. So that's the way it's kind of put together. So I mentioned that bridge sits in a pocket right here, and you've got the adjustment screws to be able to operate it. Or to be able to move it in operation. The rest of it, you've got the oil plate on the back, and we've really we're pretty proud of the fact that you can precisely control oil with this. But a lot of flexibility, a good strong die, and over time, and I almost missed it. Kind of what's happened over time, we talking about running a stiff brick. Folks are kind of running stiffer and stiffer than what they did at one time, and what it means is really having to have a stronger die to be able to do that, and one that lubricates better is good. And so how about this? Kind of the generally what we offer on dies is a K die with a die base with a shaper cap on the front. It's simple. It's relatively inexpensive, and for the folks, some folks love them today. If you want something that's stronger and probably has got more precise oil control and some features that make it more user-friendly, there's an L die available. And we've had good success with a wide range of products on these, but that's basically what we do. And we can make a whole, all sorts of different sizes, and everything from doing some ribbon dies for thin dies to some big units, so a lot of flexibility with that similar concept. Jim, I want to show the guys one more thing. If and we might have to jump out of this one, and I think I've got it in one that Steve did. He dropped a slide or two in that I'd love to share with everybody before we talk about maintenance. So let's go back to that folder again. And we can keep this one open if you want to, but the one that's labeled Steve update on the top up there. Let's see if that'll open. And I should have, and let's scroll down towards the end because most of them are similar. There are just a couple new ones in here at the very end.
Oh, way down?
Yeah. We're getting there. A little further. A little more. Okay, there we go. And so what I wanted to show the guys is, let's look right here.
That one?
Yep. And so it's only 2 slides in here. All right. So here's another one that's just good. So how about this? Everybody, so what I wanted you to take away today is us talking about die balance. If there's die balance, and we talked about lubrication playing into that, that's really what I want. If I'm planting a seed today, that's what I really want to plant. We talked a little bit about silicon carbide cores. Now then, where that fits in is getting better value for your money and longer life. All right. I didn't talk about it, but a ceramic line shaper cap as opposed to a chrome shaper cap. That's really a better value, and you can run more brick and it's going to last longer. A ceramic line shaper cap, you can't take a screwdriver and pry on it. You'll pop those ceramic plates. But that's going to extend life. And I just wanted to, Steve Durham, who's handling our die sales now, and a lot of you probably have talked to on the phone, I wanted him to put in some a couple slides on something that we're doing new on our bridges that's really nice. And again, it really isn't about die balance. This is about managing wear. So we'll put that on that side of our discussion. So does that look familiar to anybody? If you pulled a bridge out and the bridge is starting to wear or not pretty close to being gone, so you've got where that clay is kind of impinging, is that die base tapers down. You can obviously see that clay is kind of impinging and wearing into those pins here. And then if you look back at the back on this, you can also see some deterioration on this bridge bar. And it looks like, yes, so these are about gone here, and I don't know if this is obviously 2 different bridges, but you see a different version of the same thing in that slide. So what can we do about that? So you see where that wear is occurring, and Jim, let's go to the next slide in there. And so we've come up with, or kind of started using a couple additional coatings. And I don't know, I need to, for the Arkansas guys, I don't know if we need to call this a razorback coating or what. It is rough and it is ugly, but it is not. When we do a bridge, we apply tungsten carbide coating to it. You flame spray it. You got to heat it up, get it red hot, and then you spray this stuff on there, and then you got to fuse it you've got to fuse it in. And it kind of makes a nice, pretty smooth coating. What we've got is a couple of different coatings, and where we've been doing that is we've been applying that to the leading edge of a bridge bar, the exit of a bridge bar on the top and the bottom at the core pin location. So if you see, it looks like to me, this is one Steve took a picture of, and we did that leading edge. But I'm not kidding you, we've had applications to where we've doubled the life of bridges by going in and selectively applying this coating to those bridge bars. And so there's another one that if everybody's figuring out how do you stretch a dollar further today, and this is where I was like, George can help you. What we'd want to do, I'd love to take that challenge with any of the bridges that you're running if you want to try one. I've got the confidence that I think we could extend your bridge life, but these coatings have made a remarkable difference in the life, in bridge life. But it's funny. It just has got it's just got a completely different look to it than what the traditional flame spray bridges do.
Does it significantly affect your dye balance?
Well, it's a good question.
It's a lot rougher.
It's a good question, and it's something that I was like everything. If I make a change, I'd like to make one change, and I'd like to see what the result is. And my answer is we have not had issues with anybody, but I really think that the potential is there. So I would be mindful of it if you try something. So you ask a very good question. But it was just something. It's something new we're doing. And again, if you're trying to kind of do better with spending your dollars and everything, we've been really happy with the results that we've had out of this. So, all right. And Jim, the next one. But I think we probably, I think we're back into. We dropped those in, and so I should have transferred those over in the one that we've been working from. So if we close that presentation and we go back to the other one, all right, and then we'll just go, yep, great, and we'll go to the next slide. And then, and so everybody's figuring out, I dropped that one in, everybody's figuring out how to make thin brick, right? So we've made some dies to where you can score them and score those things and break them. This was actually, I'm trying to think, that's a regular brick, and here's one to where you could make two thin brick, and anyway, you can do a lot of different things if you're trying to figure out how to. That seems to be the one aspect of in a lot of areas of the country where everybody's trying to be able to be more efficient making a thin brick or make them without necessarily having to saw them. All right, and there's a half brick. I don't know if that took off or not, but somebody was trying to do, so you put it in, score them, and so you can break it in half clean, and then.
Is anyone in here doing that? I mean, or regularly? I mean, is this something you guys know about? Have you been doing it at all? At Elgin we have. We certainly experimented with it, and yes, it does work. It absolutely works, and it takes a little bit of, figuring out how deep to score them and all that good stuff, but it does work, and it'll make a good thin brick.
And the interesting thing is I just think it almost seems like thin brick is coming everywhere now. That if you were making to me, a lot of the architectural guys that are making the schools and the banks and everything else, they had to be able to supply thin brick, and it just seems like it's trickling everywhere. So. Well, and it's funny. It's like I think it's good for the brick. On one level, it's good for the brick makers because I think the margins are good on that product. But the market's changing a little bit. So everybody seems to be talking about thin brick now. So anyway, there's some options for being able to extrude them, and what you'd like to do if you could make them in a clean way. But everybody's got different equipment to work with, different setting patterns, different setting equipment. And so you kind of have to take every plan on its own to say, okay, well, what can we do? But we've come up with some kind of creative ideas. And George, flip one more. I think there's another one, to where, we did that design for somebody to where literally you could get 3 pieces on the top and 2 off the sides, and everything breaks away. But I think at thin brick, I've had people tell me thin brick they are paid twice as much per piece for a thin brick as opposed to a full size brick. Doesn't that seem crazy? Anyway,
just multiple faces on the same piece level.
The way that one is made, that's exactly right. That's right.
Is that an actual frog that you made?
We have made that one, yes. Yeah. Yep. Okay. Now then, George, you ready? We're going to switch up, and George is going to finish by talking about maintenance. Again, I was like an hour ahead of myself, and we're actually doing okay, I think, so far. Y'all want to? Yeah, are y'all ready? Would y'all be better if we took a 10-minute break? Bathroom, stretch your legs, and come back in. We'll go for about 40 minutes, and we're going to be done at noon. How about that? So, good?